For centuries, humans have looked up at the night sky and asked the same question. What is really out there? From strange lights moving against the stars to invisible forces shaping the universe, the cosmos has never stopped hiding secrets from us. Some mysteries were once thought to be beyond human understanding. Dark matter, black holes, the birth of the universe itself. Ideas so strange they sounded like science fiction. Yet today, with powerful telescopes and bold theories, we're finally starting to peel back the curtain. But every answer unlocks an even bigger question. Why does the universe expand? What existed before time began? And are we truly alone, or just one tiny spark in a vast cosmic ocean? Do not forget to leave a like and subscribe to the channel, because in this video, we dive into the biggest mysteries of the cosmos, the questions that haunted scientists for generations, and explore how modern science is finally solving them. Stay with us, because the universe is far stranger and far more incredible than you've ever imagined. Get ready, we begin. Section 1. The signal that shouldn't exist. In 1977, a radio telescope in Ohio picked up a signal from space that was so powerful, so precisely tuned, and so utterly anomalous that the astronomer who discovered it wrote "wow" in the margins of the printout. That annotation gave the signal its name, and for 46 years, the WOW signal remained one of the most compelling pieces of evidence that we might not be alone in the universe. It lasted exactly 72 seconds. It came from the direction of the constellation Sagittarius, and it was broadcast at a frequency that's internationally protected for scientific observation because it's the same frequency that hydrogen emits naturally in space. Which meant that if someone or something out there wanted to send a message that would be heard across the galaxy, this would be exactly the frequency they'd choose. The problem? The signal never repeated. Not once in 46 years of listening. Astronomers pointed dozens of radio telescopes at that same patch of sky, waiting, hoping, analysing every whisper of electromagnetic radiation that drifted through. Nothing. Just silence. Some scientists argued it must have been a satellite glitch, a reflection, some kind of terrestrial interference that somehow mimicked an extraterrestrial broadcast. Others refused to accept that explanation, pointing out that no known satellite or aircraft could produce a signal with those exact characteristics from that precise celestial location. The mystery deepened when researchers realized that the signal had swept through frequencies in a pattern that suggested it was coming from an object moving through space, something that would be impossible for a stationary satellite to produce. Debates raged in academic journals. Careers were built and demolished on interpretations of that single 72-second burst of radio waves. But here's what changed everything. In 2020, an amateur astronomer named Alberto Caballero decided to do something that professional researchers somehow hadn't thought to do in 43 years. He used data from the European Space Agency's Gaia satellite, which had been mapping the precise locations and movements of over 1 billion stars in our galaxy. And he searched for sun-like stars in the exact region where the WOW signal originated. What he found was extraordinary. In that vast field of stars, there was exactly one star that matched the profile of our own sun. A star with the right temperature, the right size, the right composition to potentially harbour planets in its habitable zone. A star that, until Gaia's unprecedented mapping project, we didn't even know existed because it was too far away and too faint for earlier surveys to detect. Then in 2022, another team made an even more startling discovery. Using archived data from the now defunct Arecibo telescope, they found evidence that suggested the WOW signal might not have been a one-time event after all. Hidden in decades of data that had never been fully processed because of the sheer volume of information the telescope collected, there were hints of similar signals, much weaker, occurring at irregular intervals from the same region of space. The signals weren't identical to the WOW signal, but they shared certain characteristics: the same narrow frequency band, the same duration patterns, the same apparent Doppler shift that indicated movement. The reason these signals had been missed for so long was that they were operating at the very edge of detectability, like someone whispering from across a crowded room. You'd only hear them if you knew exactly when and where to listen. But then the real breakthrough came. In 2023, a team of astrophysicists at the University of Puerto Rico published a paper that changed everything we thought we knew about the WOW signal. They had been studying a particular type of cosmic event called a magnetar flare, which occurs when a neutron star with an impossibly powerful magnetic field suddenly releases an enormous burst of energy. These flares are rare, violent, and can broadcast across a wide spectrum of frequencies. The team built a computer model to simulate what a magnetar flare would look like if it occurred at exactly the right distance and angle to Earth, and if certain conditions in the interstellar medium caused the signal to be narrowed and focused by natural cosmic phenomena. The result was almost identical to the WOW signal, not similar, almost identical. Every characteristic matched: the frequency, the duration, the intensity curve, even the way it swept through the radio spectrum. The mystery appeared to be solved. The WOW signal wasn't a message from an alien civilization. It was an incredibly rare natural phenomenon, a cosmic fluke that happened to mimic exactly what we would expect an intelligent transmission to look like. The 1 in a billion chance that a magnetar flare would occur at precisely the right moment, at precisely the right distance, with precisely the right interstellar conditions to produce a signal indistinguishable from an artificial broadcast. Case closed. Mystery solved. Except for one problem. When the team tried to verify their findings by searching for the magnetar that should have produced the flare, they couldn't find it. They scanned the region with X-ray telescopes, infrared arrays, and optical instruments. Nothing. No magnetar. No neutron star. No stellar remnant of any kind in that area of space. Which meant either their entire explanation was wrong, or there was a magnetar out there that somehow became invisible immediately after producing the most famous radio signal in astronomical history. And that's where things get strange, because in early 2024, another research team proposed an alternative explanation that sounds like science fiction but is rooted in legitimate physics. They suggested that what we detected in 1977 wasn't a signal from our universe at all. It was a signal from another universe, briefly making contact with ours through a phenomenon predicted by string theory called a cosmic membrane collision. In this model, our universe exists on a three-dimensional membrane floating in a higher dimensional space, and occasionally these membranes can come close enough to interact. If that happened in 1977, if two universes briefly touched, the energy released at the point of contact could produce exactly the kind of signal we detected. And it would explain why we've never seen it again, why there's no source object in that region of space, and why the signal had characteristics that still don't perfectly match any known natural phenomenon in our cosmos. The truth is, we still don't know. 47 years later, with all our advanced technology, all our theoretical physics, all our computational power, we still cannot say with absolute certainty what caused that 72-second burst of radio waves from deep space. Was it a magnetar we can't find? Was it the whisper of another universe? Or was it something else entirely, something we haven't even conceived of yet? The wow. Signal remains officially unexplained, a reminder that even our most sophisticated explanations can leave questions unanswered, and that sometimes the cosmos refuses to give up its secrets easily. Section 2. The planet that shouldn't be there. In 2004, astronomers discovered something that broke the rules of planetary formation. They found a planet orbiting a star called Fomalhaut, about 25 light-years from Earth. That discovery should have been routine. We'd been finding exoplanets for nearly a decade by that point, and we were getting pretty good at it. But Fomalhaut B, as the planet was designated, was different in a way that made scientists deeply uncomfortable. It was orbiting inside a ring of debris, a massive belt of dust and ice that surrounds the star like a cosmic donut. And according to every model of how solar systems form, that should have been impossible. Planets either clear out their orbital paths by consuming or ejecting debris, or they fail to form at all. There's no middle ground. Yet here was Fomalhaut B, gliding serenely through a ring of material that should have either prevented its formation or been swept away by its gravity. But that was just the beginning of the strangeness. When astronomers tried to study the planet more closely, they realized something was very wrong. The planet was bright in visible light, much brighter than any planet should be. Gas giants like Jupiter are relatively dark because they don't reflect much sunlight and don't generate their own visible light. Rocky planets can be brighter, but they're typically too small to see at 25 light-years distance. Fomalhaut B was bright enough to see clearly with the Hubble Space Telescope, which meant either it was covered in something extraordinarily reflective or something else was going on. Astronomers tried to detect the planet's heat signature using infrared telescopes, the standard method for confirming the presence of a large planet. They found nothing. No infrared signal whatsoever. A planet the size of Jupiter should be radiating enormous amounts of heat, visible even across interstellar distances. Fomalhaut B was radiating nothing. Over the next decade, the mystery deepened. Multiple observation campaigns tracked the planet as it moved through its orbit, and astronomers noticed something that shouldn't happen. The planet's brightness was changing. Not in a predictable pattern like you'd expect from a rotating planet with different surface features, but erratically, dramatically, as if the planet itself was expanding and contracting. By 2012, some researchers were starting to question whether Fomalhaut B was a planet at all. Alternative theories emerged, each more exotic than the last. Maybe it was a massive ring system surrounding a smaller planet, though that wouldn't explain the infrared. Problem: maybe it was a recent collision between two large planetary bodies, creating a vast cloud of reflective debris that happened to look like a single object, though the mathematics of that scenario were incredibly unlikely. Maybe it was something else entirely, some new class of astronomical object that we'd never encountered before. Then in 2020, astronomers made an announcement that shocked the astronomical community. Fomalhaut B had disappeared. New observations with Hubble showed absolutely nothing where the planet should have been. One of the most studied exoplanets in the sky, an object that had been observed dozens of times over 16 years, had simply vanished. The scientific paper announcing the disappearance had a conclusion that sounded more like fantasy than fact. Fomalhaut b was never a planet. It was the aftermath of a catastrophic collision between two ice-rich planetesimals, objects similar to large comets or dwarf planets in our own Kuiper belt. The collision had created an enormous expanding cloud of dust and ice crystals, held together temporarily by electrostatic forces and mutual gravity. What we had been watching for 16 years wasn't a planet at all. It was a debris cloud slowly dissipating into space, gradually spreading out until it became too diffuse to see. The mystery was solved, except it wasn't, because here's what the disappearance theory doesn't explain. When astronomers went back through all the archived observations of Fomalhaut b, they noticed something that the collision hypothesis couldn't account for. The object's orbit was changing in ways that a debris cloud shouldn't be able to change. Debris from a collision follows predictable trajectories based on the momentum from the impact, but Fomalhaut b's orbital path showed small but measurable deviations that suggested something was actively influencing its motion. Either there was another massive object in the system that we hadn't detected, gravitationally tugging on the debris cloud, or the debris cloud itself contained something solid enough and massive enough to alter its own trajectory. Neither explanation made much sense, and both raised more questions than they answered. Then in 2023, a team of researchers published a paper that offered a radically different explanation, one that tied together all the anomalies in a single, elegant, and deeply strange theory. They proposed that what we observed wasn't the result of a collision at all. It was a planet in the process of disintegrating, torn apart by tidal forces from Fomalhaut itself. But not just any disintegration. They suggested we had witnessed something that had never been observed before. A planet crossing the Roche limit of its star, the distance at which tidal forces become strong enough to overcome the planet's own gravity. In this scenario, Fomalhaut b had started as a real planet, possibly an ice giant like Neptune that was following an extremely elliptical orbit. Each time it swung close to its star, tidal forces stripped away more of its outer layers, creating the bright reflective cloud we observed. The planet's core remained intact for years, continuing to gravitationally influence the cloud and explain the orbital anomalies. But eventually, after decades or centuries of this process, the core itself was consumed, and the planet ceased to exist. This explanation fit the observations better than any previous theory. It explained the brightness variations as different amounts of material were stripped away during each orbital pass. It explained the lack of infrared radiation because ice and dust don't emit significant heat. It explained the changing orbit as the planet lost mass and its gravitational interaction with the star evolved. And it explained the disappearance as the final dissolution of the planetary core. But here's the unsettling part. If this explanation is correct, we witness something that should be extraordinarily rare. Planets don't just wander into death spirals around their stars by accident. Something had to have perturbed Fomalhaut b's orbit, sending it on a path that would eventually destroy it. Either there was another massive planet in the system that gravitationally scattered Fomalhaut b inward, or something else entirely caused the orbital change. A close encounter with a passing star, a collision with another planet that sent both objects into unstable orbits. Or perhaps something we haven't considered yet. The current consensus among astronomers is that we probably did witness a planetary disintegration, that Fomalhaut b was a real planet that died during the brief window of time we happened to be watching. But consensus isn't certainty. The truth is that we observed something for 16 years that defied our understanding, and when we finally developed an explanation that fit most of the facts, the object disappeared before we could verify our hypothesis. We'll never know for certain what Fomalhaut b was because it no longer exists to study. It's gone, dispersed into the vast debris ring that surrounds its star, indistinguishable from the countless other particles of dust and ice that orbit in that cosmic graveyard. All we have left are our observations, our theories, and the uncomfortable knowledge that sometimes the universe shows us something impossible, then erases it before we can figure out what we really saw. Section 3. The impossible structure. In 1991, astronomers discovered something that shouldn't exist, not in the sense that it was unexpected or unusual, but in the literal sense that according to our understanding of cosmology, it could not exist. They found a structure in space so large that it violated the fundamental principles of how the universe is supposed to work. It's called the Hercules Corona Borealis Great Wall, and it is the largest known structure in the observable universe. How large? Imagine a wall of galaxies stretching across 10 billion light-years of space. For reference, the entire observable universe is 93 billion light-years across, and this single structure occupies more than 10% of that distance. It contains billions upon billions of galaxies, each galaxy containing hundreds of billions of stars, all bound together by gravity into a single coherent structure. A structure so immense that light itself, travelling at 186,000 miles per second, takes 10 billion years to cross from one side to the other. Now here's why that's a problem. According to cosmological models, structures in the universe should follow a size limit based on how long the universe has existed and how fast information can travel through space. Think of it this way. The universe is roughly 13.8 billion years old. In that time, gravity has had a finite amount of time to pull matter together into structures like galaxies, galaxy clusters, and superclusters. There's a theoretical maximum size for any structure based on how far gravitational influence could have spread in that time, and that maximum size is approximately 1.2 billion light-years. The Hercules Corona Borealis Great Wall is more than 8 times larger than it should be possible for anything in our universe to be. It's as if someone built a skyscraper out of a material that can only support a structure 10 stories tall, but the building somehow reaches 80 stories into the sky without collapsing. It shouldn't stand, but there it is. When this structure was first discovered, most astronomers assumed it was either a statistical anomaly, a case of scientists seeing patterns where none existed, or that it would disappear with better data. Galaxy surveys in the early 1990s were nowhere near as comprehensive as they are today. Maybe the apparent structure was just a projection effect, a bunch of unrelated galaxies that happened to line up from our perspective, but weren't actually connected. But as decades passed and our observational tools improved, the Great Wall didn't disappear. It became more defined, more undeniable. In 2013, a new analysis confirmed not only that the structure was real, but that it was even larger than originally thought. The galaxies within it were genuinely gravitationally bound to each other, forming a coherent astronomical structure that spanned a distance so vast that the human mind struggles to comprehend the scale. Scientists tried to explain it away. One proposal suggested that the structure wasn't actually as large as it appeared, that there was some effect of cosmic expansion or gravitational lensing that made it look bigger than it really was. That hypothesis fell apart when researchers measured the redshifts of individual galaxies throughout the structure and confirmed that they were all at roughly the same distance from Earth, meaning the structure really did extend across billions of light years. Another theory proposed that the structure formed through an incredibly rare series of galaxy mergers, a cosmic coincidence where multiple smaller structures happened to connect over billions of years. The mathematics of that scenario showed it was possible, but only if the probability distribution of galaxy formations in the early universe was completely different from what all our other observations suggested. It would require rewriting our understanding of cosmological evolution to accommodate a single structure, which felt like explaining away one mystery by creating a dozen others. Then in 2019, a team of cosmologists proposed something radical. They suggested that the Hercules Corona Borealis Great Wall wasn't formed by normal gravitational collapse at all. Instead, it might be a relic from a phase transition in the early universe, a kind of cosmic defect that formed within the first fractions of a second after the Big Bang. In this model, the universe underwent a series of phase transitions as it cooled, similar to how water turns to ice when it reaches a certain temperature. During these transitions, imperfections could form, like the cracks that appear in ice when it freezes too quickly. These cosmic defects would create regions where matter was distributed differently, seeding the formation of structures far larger than normal gravitational processes could produce. If this explanation is correct, the Great Wall isn't just a really big collection of galaxies. It's a scar in the fabric of space, itself, a permanent mark left by the violent processes that shape the universe in its first moments of existence. But that explanation, as elegant as it sounds, comes with its own problems. Phase transition defects should be visible throughout the universe, not just in one location. If the mechanism that created the Hercules Corona Borealis Great Wall was a fundamental feature of early cosmic evolution, we should see similar structures scattered across the sky. We don't. This appears to be unique, or at least extremely rare, which suggests either our phase transition theory is incomplete or something else is happening. Some researchers have proposed that what we're seeing is evidence of a bubble collision during cosmic inflation, the brief period immediately after the Big Bang when the universe expanded faster than light. In eternal inflation theory, our universe is just one bubble in an infinite froth of universes, all expanding into a higher dimensional space. Occasionally, these bubbles collide, and when they do, they leave distinctive marks on the cosmic microwave background radiation and on the distribution of matter. The Great Wall could be one of those marks, a cosmic bruise where our universe bumped into another. That brings us to something even more unsettling. In 2022, astronomers discovered another structure that rivals the Hercules Corona Borealis Great Wall in size. It's called the Giant Arc, and it spans approximately 3.3 billion light-years of space. On its own, that would be fascinating, but not necessarily revolutionary. The disturbing part is its orientation. The Giant Arc appears to be aligned with another enormous structure called the Giant Ring, which was discovered in 2024 and spans roughly 1.3 billion light-years. These structures are not randomly oriented. They appear to be geometrically related, as if they're part of some larger pattern that we can only see fragments of. It's like finding two pieces of an enormous puzzle and realizing they fit together, but you have no idea what the complete picture looks like or how many pieces are missing. This is where our comfortable assumptions about the universe start to crumble. The cosmological principle, one of the foundational assumptions of modern astronomy, states that the universe should look roughly the same in all directions when viewed at large enough scales. There shouldn't be preferred directions or alignments. Everything should be more or less isotropic and homogeneous, meaning uniform and evenly distributed. But these massive structures violate that principle. They suggest that there are patterns in the universe at scales far larger than we thought possible, patterns that our current theories cannot explain. Either the cosmological principle is wrong, which would require throwing out a century of theoretical work and starting over, or there's something about the early universe that we fundamentally misunderstand, something that allowed these impossibly large structures to form. The current scientific consensus, to the extent that one exists, is that we're missing something big in our cosmological models. Most researchers believe these structures are real and not observational artifacts, which means our theories need revision. But revising fundamental cosmological theories is not like updating a phone app. It requires reconsidering decades of work, reanalyzing countless observations, and potentially accepting that our entire framework for understanding the universe's evolution might be incomplete. Some scientists are exploring modified theories of gravity that would allow larger structures to form without violating other observational constraints. Others are investigating whether dark energy, the mysterious force driving the universe's accelerating expansion, might have behaved differently in the early universe, affecting how matter clumped together. Still others are considering whether we need to abandon the Big Bang model altogether in favour of a cyclic universe that contracts and expands eternally, where these massive structures are remnants from previous cosmic cycles. What's clear is that the existence of these impossibly large structures is not a minor anomaly. It's a fundamental challenge to our understanding of cosmology, one that has no easy resolution. And here's what makes this mystery particularly profound. These structures are not hypothetical or inferred from complex calculations. We can see them, we can photograph them, we can measure their properties with incredible precision. They are empirically undeniable facts about our universe, facts that our best theories cannot accommodate. It's as if the cosmos itself is telling us that we've got something fundamentally wrong about how reality works at the largest scales, but it's not telling us what we've gotten wrong or how to fix it. We're left with observations that contradict theory, theories that contradict observations, and the uncomfortable awareness that the universe might be stranger and more structured than we ever imagined. The Hercules Corona Borealis, Great Wall, still exists, still spans 10 billion light-years of space, still contains more mass than 1 trillion Milky Way galaxies, and still should not be possible according to everything we thought we knew about cosmology. Its existence is a solved mystery only in the sense that we now know it's definitely there. Why it's there, how it got there, and what it means for our understanding of the cosmos remain questions without answers. Sometimes solving a mystery just means confirming that reality is weirder than our theories allow, and accepting that the universe doesn't care about our carefully constructed models of how it's supposed to work. Section 4. The light that came from nothing. On October 9th, 2022, astronomers detected a burst of gamma rays from deep space that was so powerful it temporarily blinded satellites, disrupted Earth's ionosphere, and remains the brightest cosmic event ever recorded in human history. They called it GRB 2021-9A, a designation that sounds mundane but represents something extraordinary. For 10 minutes, this single event was brighter than all the other gamma-ray sources in the universe combined. It released more energy in those 10 minutes than our Sun will produce in its entire 10 billion-year lifetime. And it came from a galaxy so far away that the light reaching us had been travelling for 1.9 billion years, meaning we were seeing an event that occurred when the most complex life on Earth was still single-celled organisms floating in ancient oceans. Gamma-ray bursts are not new phenomena. We've been detecting them since the 1960s, when military satellites designed to monitor nuclear weapons tests started picking up mysterious flashes of high-energy radiation from random directions in space. It took decades to figure out what was causing them, but eventually astronomers determined that most gamma-ray bursts come from one of two sources: the collision of neutron stars or the collapse of massive stars into black holes. Both processes release enormous amounts of energy in the form of jets of matter and radiation that shoot out at nearly the speed of light. If one of these jets happens to point toward Earth, we see a gamma-ray burst. They're cosmic lighthouses, visible across billions of light years if you happen to be standing in their beam. But GRB 2020-1009A was different in ways that made scientists question everything they thought they understood about these events. First, the energy output was orders of magnitude higher than any previously recorded gamma-ray burst. Not just a little brighter, but so much brighter that it didn't fit on the same scale as other events. Second, the burst lasted far longer than typical gamma-ray bursts, which usually flash for a few seconds at most before fading. This one kept going for 10 minutes, pulsing and flickering in patterns that suggested something complex was happening at the source. Third, and most puzzling, the burst was accompanied by the highest energy photons ever detected from a cosmic source. Photons with energies approaching 18 tera electron volts. To put that in perspective, these individual particles of light carried about as much energy as a flying mosquito, which sounds trivial until you remember that mosquitoes are millions of times larger than photons. Concentrating that much energy into something as small as a photon requires physics operating at the absolute edge of what the universe allows. Within hours of the burst's detection, observatories around the world turned their instruments toward the source location, trying to understand what had caused such an unprecedented event. They found the afterglow, the fading radiation that lingers after a gamma-ray burst, exactly where theoretical models predicted it should be based on the burst's distance and energy. That was reassuring. It meant the burst followed at least some of the expected physics. But then they started looking for the source itself, the dying star or colliding neutron stars that should have produced the burst. And they found something that made no sense whatsoever. There was nothing there. No supernova remnant, no black hole accretion disk, no sign of the catastrophic stellar death that should have generated such an enormous release of energy. The afterglow was fading as expected, but the source object that should have been visible underneath it, the smoking gun that would explain what happened, simply didn't exist. Astronomers scrambled to explain the absence. Maybe the source was obscured by dust, though the X-ray and infrared observations should have penetrated any dust cloud. Maybe the burst came from a particularly unusual star that didn't leave a visible remnant, though no theoretical models predicted such an outcome. Maybe the explosion was so energetic that it completely vaporized the source object, though that would require energy levels even higher than what we observed. Each explanation had problems, and none of them felt quite right. The scientific papers published in the months following the burst were filled with cautious language and hedged conclusions, the kind of writing that appears when scientists know something significant has happened but don't yet have a framework to understand it. Then in mid-2023, a breakthrough came from an unexpected direction. A team of cosmologists who normally study the early universe noticed something peculiar about the gamma-ray burst's spectrum. the distribution of energy across different frequencies. Buried in the data was a pattern that looked suspiciously similar to something they had been studying in their cosmic microwave background research: the signature of quantum fluctuations in a fundamental field that permeates all of space. This field, if it exists, would be a remnant from the first moments after the Big Bang, a kind of cosmic scaffolding that influenced how matter and energy behaved in the early universe. Most physicists believe this field decayed away billions of years ago. Its energy dissipated into other forms. But what if it didn't? What if pockets of this primordial field still exist, invisible and undetectable until something disturbs them? The team proposed something that sounded like science fiction. GRB 222109A might have been caused by the annihilation of a primordial field bubble. In this scenario, somewhere in deep space, a pocket of this ancient field that had somehow survived for billions of years suddenly underwent a phase transition, similar to how a supercooled liquid suddenly freezes when disturbed. The energy stored in that field bubble would be released instantaneously, producing exactly the kind of high-energy burst we observed. And because the field itself would be invisible until it decayed, there would be no source object to find afterwards, nothing left behind except the radiation that reached our telescopes. The charter mystery of the missing source wasn't a mystery at all. We were looking for something that never existed in the conventional sense, trying to find the physical remains of a purely energetic phenomenon. This explanation was elegant, but it came with profound implications. If primordial field bubbles exist and can decay spontaneously, they represent a fundamental instability in the fabric of space itself. These bubbles could be scattered throughout the universe, ticking time bombs of unimaginable energy that could release their contents at any moment. The universe we inhabit might be riddled with them, invisible threats that could sterilize entire regions of space without warning. And we would have no way to detect them before they burst, no way to predict where or when the next one might decay. Every gamma-ray burst we've ever observed might not be the death of a star, but the collapse of a pocket of primordial energy, which would mean our entire understanding of these events needs to be reconsidered. But here's where the explanation gets truly disturbing. If these field bubbles exist, they don't just pose a threat to distant galaxies. They could exist in our own galaxy, in our own cosmic neighborhood, anywhere that conditions allowed a pocket of primordial field to survive from the early universe until now. A nearby bubble collapse would be catastrophic in ways that are difficult to articulate. The gamma radiation alone would strip away Earth's ozone layer within seconds, exposing the surface to sterilizing solar ultraviolet radiation. The high-energy particles would generate a cascade of secondary radiation in our atmosphere, creating a spike in mutation-causing radiation that would affect every living organism on the planet. And if the bubble was close enough, the sheer energy density could trigger runaway particle production in our atmosphere, essentially igniting the air itself in a chain reaction that would be visible from space as the planet briefly glowed like a small star. Life on Earth would not survive such an event. Of course, the probability of a nearby bubble collapse is extraordinarily small, so small that it's not worth losing sleep over. But it's not zero, and that's what makes this mystery so existentially unsettling. We live in a universe where pockets of unimaginable energy might be lurking invisibly in the vacuum of space, where the very fabric of reality could be unstable in ways we cannot detect or predict. GRB 221009A gave us a glimpse of what happens when one of these pockets decays, and it was bright enough to affect Earth from 1.9 billion light-years away. If one existed in our galaxy and decayed, the consequences would be beyond imagining. The scientific consensus as of now is that the primordial field bubble hypothesis is intriguing but not confirmed. Most astronomers still lean toward a more conventional explanation, suggesting that GRB 22-1009a was produced by an unusually massive star collapsing in an unusually energetic way, and that the missing source object is simply too faint to detect with current instruments. But the lack of a visible supernova or black hole in the expected location remains unexplained, and alternative theories continue to gain traction as more data is analysed. What we know for certain is that on October 9th, 2022, something released more energy in 10 minutes than our Sun will produce in 10 billion years, and we still cannot say with complete confidence what that something was or whether it could happen again. The mystery of GRB 22-1009a is technically solved in the sense that we have plausible explanations for what caused it, but those explanations open up new mysteries that might be even more troubling than the original question. Sometimes the answer to a cosmic mystery is not a resolution, but a revelation that the universe is more dangerous, more unpredictable, and more fundamentally uncertain than we wanted to believe. And sometimes the brightest light in recorded history doesn't illuminate the darkness. It just shows us how much deeper that darkness really goes. Section 5. The anomaly at the edge of time. There is a galaxy that shouldn't exist, not because it's unusual or unexpected, but because it formed so early in the universe's history that its existence contradicts our timeline of cosmic evolution. It's called GNZ11, and it holds the distinction of being one of the most distant galaxies ever observed, sitting at a distance of 13.4 billion light-years from Earth. When we look at GNZ11, we're seeing light that has been travelling through space for 13.4 billion years, which means we're seeing this galaxy as it existed just 400 million years after the Big Bang. That's extraordinarily early in cosmic terms, so early that the universe was barely 3% of its current age. And yet, this galaxy is not a tiny, primitive collection of stars struggling to form in the primordial darkness. It's a fully mature galaxy containing roughly 1 billion stars, actively forming new stars at a rate 20 times faster than the Milky Way, and showing signs of chemical enrichment that should take billions of years to develop. Here's why that's impossible according to our standard cosmological model. In the immediate aftermath of the Big Bang, the universe consisted of hydrogen, helium, and trace amounts of lithium. That's it. No heavier elements existed because the universe hadn't been around long enough for stars to form, fuse elements in their cores, and explode as supernovae to scatter those elements into space. The first stars, called population 3 stars, would have been enormous, short-lived, and composed entirely of primordial elements. When these first stars died, they seeded the cosmos with heavier elements like carbon, oxygen, and iron. Then a second generation of stars formed from gas clouds enriched with these new elements, and those stars produced even more heavy elements when they died. This process continues across billions of years, gradually increasing the metallicity of galaxies. It's a slow, stepwise progression that requires multiple generations of stellar evolution. You cannot skip steps. You cannot have a galaxy rich in heavy elements without first having billions of years of star formation and death to produce those elements. GNZ11 breaks this timeline. Spectroscopic analysis of the galaxy's light reveals the presence of oxygen, carbon, and other heavy elements in significant quantities, elements that should not exist in appreciable amounts just 400 million years after the Big Bang. The galaxy's stellar population appears to be multiple generations deep, with older red stars coexisting alongside young blue stars, suggesting that star formation in this galaxy began even earlier than we can currently observe. Everything about GNZ 11 suggests it should be billions of years older than the universe allows it to be. It's as if you found a fully grown oak tree on a plot of land that was only cleared last month. The timeline doesn't work. Something is wrong with either our observations, our theories, or our understanding of how time itself functions in the early universe. When GNZ 11 was first discovered in 2016 using the Hubble Space Telescope, many astronomers assumed there was a measurement error. The galaxy's distance might have been miscalculated, or the spectral lines indicating heavy elements might have been misidentified. But subsequent observations with multiple independent instruments confirmed the initial findings. The galaxy really was that distant, that old, and that chemically mature. The scientific papers describing GNZ 11 used carefully worded language acknowledging the tension between observations and theory, but stopped short of claiming the galaxy was impossible. Instead, they suggested that models of early galaxy formation might need revision, that perhaps star formation in the early universe was more efficient than we thought, or that the first stars were more massive and died more quickly than current models predicted. Then in 2022, the James Webb Space Telescope began operations and turned its infrared eye toward the distant universe. What it found was not a single impossible galaxy, but dozens of them. Galaxies at similar distances to GNZ 11. Galaxies formed in the first 500 million years of cosmic history, all showing signs of unexpected maturity. Some were even more massive than GNZ 11, containing billions of stars in configurations that looked suspiciously like modern spiral and elliptical galaxies, rather than the irregular, chaotic proto-galaxies that should have dominated the early universe. The problem was no longer an anomaly, it was a pattern, a systematic discrepancy between what we observe and what our theories predict. The scientific community responded with a flurry of proposed explanations. One hypothesis suggested that the first stars were far more massive than we thought, perhaps hundreds of times the mass of our Sun, and that these hypermassive stars burned through their fuel and exploded as supernovae within just a few million years instead of hundreds of millions. If the first generation of stars lived and died much faster than expected, they could have enriched the cosmos with heavy elements far earlier in cosmic history, allowing mature galaxies like GNZ 11 to form on accelerated timelines. Computer simulations of this scenario showed it was plausible, but it required adjusting numerous parameters in stellar evolution models, parameters that were based on decades of observations of stars in our own galaxy. The models could be made to work, but only by assuming that stars in the early universe behaved fundamentally differently from stars today, a conclusion that was theoretically possible but empirically unverified. Another explanation invoked dark matter, the invisible substance that makes up 85% of all matter in the universe. Standard models assume dark matter is cold, meaning its particles move relatively slowly and gradually clump together to form the gravitational scaffolding around which normal matter collapses to form galaxies. But what if dark matter in the early universe was warmer, with particles moving faster and clumping together more quickly? Warm dark matter would allow structures to form earlier than cold dark matter models predict, potentially explaining why galaxies like GNZ 11 appear so mature at such early times. The problem with this explanation is that warm dark matter has other observational consequences that we haven't seen, like a suppression of small-scale structure formation that should be visible in surveys of nearby dwarf galaxies. The universe today doesn't look like a warm dark matter universe should look, which means if dark matter was warm in the early universe, it somehow transitioned to cold later on, a scenario that requires new physics we don't currently have. Then there's the explanation that nobody wanted to confront, but that was becoming harder to ignore. What if our measurements of cosmic age are wrong? The age of the universe is calculated based on the expansion rate, which we measure using a variety of methods, including observations of the cosmic microwave background, supernova distances, and local measurements of galaxy motion. All of these methods agree within a few percent that the universe is approximately 13.8 billion years old. But what if there's a systematic error affecting all of these measurements? What if the universe is actually older than we think, giving more time for galaxies like GNZ11 to evolve? This sounds like an easy solution until you realize that making the universe significantly older would break dozens of other observations that depend on the current age estimate. The abundances of light elements produced in the Big Bang, the temperature and structure of the cosmic microwave background, the evolution of galaxy populations across cosmic time, all of these would need to be recalibrated, and many of them would stop making sense if the universe's age changed by more than a few percent. You can't fix one problem without creating 10 others. By 2024, a new and rather unsettling hypothesis began gaining traction among theoretical cosmologists. They proposed that GNZ11 and similar early galaxies might be evidence of primordial black holes, seeding galaxy formation far earlier than conventional processes would allow. Primordial black holes are hypothetical objects that could have formed in the first second after the Big Bang from density fluctuations in the early universe. Unlike black holes formed from stellar collapse, primordial black holes could have any mass, from subatomic to millions of times the mass of the Sun. If supermassive primordial black holes existed in the early universe, they would act as gravitational anchors, pulling in surrounding gas and triggering star formation long before normal processes could get started. This would explain how galaxies form so quickly and why they appear so mature, but it requires primordial black holes to exist in the first place, something we've never detected, and that remains purely theoretical. What makes this explanation particularly intriguing is that it connects to another cosmic mystery, the existence of supermassive black holes in the early universe. Observations have found black holes with masses of 1 billion suns in galaxies that formed less than 1 billion years after the Big Bang, and there's no good explanation for how these black holes grew so large so quickly. Normal growth processes would take billions of years to accumulate that much mass, even under ideal conditions. Primordial black holes would solve both mysteries at once, explaining both the early galaxies and the early supermassive black holes as consequences of the same underlying phenomenon. It's an elegant solution that ties together multiple anomalies with a single mechanism, which is usually a good sign that you're on the right track. But it's also untestable with current technology, since primordial black holes, if they exist, would be indistinguishable from black holes formed by other processes. So where does that leave us? As of now, GNZ11 and its impossible siblings remain officially unexplained. We have multiple hypotheses that could account for their existence, but no consensus on which is correct, and no definitive observations that rule out the alternatives. What we know for certain is that galaxies in the early universe are not behaving the way our models predict they should. Either star formation was vastly more efficient in the early cosmos than we thought, or dark matter behaves differently than we assumed, or primordial black hole-seeded galaxy formation, or the universe is older than we calculated, or something else entirely is happening that we haven't even considered yet. Each possibility requires rethinking fundamental aspects of cosmology, and none of them is without significant theoretical challenges. The mystery of GNZ11 is emblematic of a larger problem in modern astronomy. The more powerful our telescopes become, the more discrepancies we find between theory and observation. The universe at cosmic dawn, the period when the first stars and galaxies formed, looks nothing like we predicted it would look. It's too structured, too organized, too mature. Everything happened faster than it should have, as if the early universe was running at double speed while our theories were calibrated for normal time. And that raises a question that strikes at the heart of cosmology. If we're this wrong about the early universe, what else are we wrong about? How many other fundamental assumptions are waiting to be overturned by the next generation of observations? The biggest mysteries of the cosmos are being solved, but the solutions are revealing that the universe is stranger than we imagined, governed by processes we don't fully understand, shaped by forces we're only beginning to recognize. GNZ11 sits at the edge of observable space and the edge of observable time, a galaxy that shouldn't exist, showing us that the universe doesn't care about our models. It is what it is, regardless of what our theories say it should be. And sometimes the most humbling realization in science is that nature is under no obligation to make sense to us, that the cosmos operates according to rules we might never fully comprehend, and that the boundary between solved mysteries and new enigmas is far thinner than we'd like to believe. We've travelled across 13 billion years of cosmic history, from radio signals that whisper across the void to galaxies that defy the limits of time itself. We've examined planets that disappeared before our eyes, structures too large to exist, and bursts of energy that rewrote our understanding of what's possible in the universe. And in each case, we found answers. But those answers opened doors to rooms we didn't know existed, revealing corridors of ignorance stretching far beyond what we'd solved. This is the nature of cosmic mysteries. We solve them not by reaching a final definitive answer, but by replacing old questions with new ones, by trading comfortable ignorance for uncomfortable knowledge. We learned that the wow signal might have been a magnet or flare from a source we can't find, or a whisper from another universe briefly touching our own. We discovered that Fomalhaut b was likely a planet tearing itself apart, a slow-motion death that we witnessed by accident during the cosmic eye blink of human observation. We confirmed that the largest structure in the universe shouldn't be able to exist according to our cosmological models, yet it spans 10 billion light-years regardless of what our equations say. We found that the brightest burst of energy in recorded history came from something we still can't fully explain, possibly a pocket of primordial energy collapsing after surviving for billions of years. And we realized that the early universe was producing mature galaxies, impossibly fast, as if time itself operated differently in the cosmic dawn. These are the mysteries we've solved, and they've taught us something profound. The universe doesn't owe us explanations. It simply exists, operating according to principles that occasionally align with our theories, and just as often diverge from them in ways that challenge everything we think we understand. The cosmos is not a puzzle designed for us to solve. It's a reality we're trying to comprehend with brains that evolved to hunt prey and avoid predators on an African savanna, using mathematics we invented to describe the world we can see and touch, extending those tools into realms where intuition fails and common sense becomes a liability. And yet we persist. We build bigger telescopes, develop more sophisticated theories, collect more data, and inch closer to understanding. Not because we expect to find all the answers, but because the questions themselves are worth asking. Because every mystery we solve, no matter how unsettling the solution, expands the boundary of human knowledge just a little further into the unknown. Because somewhere in the pattern of galaxies and gamma rays and gravitational waves, there's a truth about existence itself waiting to be discovered. The biggest mysteries of the cosmos are being solved. But the universe is vast, reality is strange, and for every door we open, two more appear at the end of the hallway. The cosmic detective story continues, and we're only beginning to understand the plot. The night sky still holds secrets, and some of those secrets, when finally revealed, will change everything we think we know about where we came from, what we are, and where we're going. The mysteries continue, the cosmos waits, and somewhere out there, beyond the edge of what we can see, the universe is preparing its next impossible revelation.